Today, on how it's made. Metal golf clubs. Waffles. Custom wires and cables. And train wheels. Golfers use different types of clubs for different types of shots. Woods for long-distance shots off a tee, putters to gently roll the ball into the cup, and irons for everything in between. That's why in golf, choosing the right club for the shot is a key part of the game strategy. The heads of these golf clubs are made from aerospace-grade stainless steel. To produce them, the factory begins with a wax replica of the club head. To make this wax pattern, as it's called, they inject hot wax into a mold. They extract the pattern and snip off the bulk of the excess wax. Using hot wax as an adhesive, a robot joins several patterns to other wax parts in the shape of gates and runners, the term for the channels that guide molten metal into the casting mold. Then the robot dips these patterns into liquid ceramic material 4 times, with a shower of silica sand in between each coat. The ceramic and sand harden, forming a shell around the wax patterns. Then the factory melts out the wax. The shell is now a mold with which to cast the metal club heads. On the casting floor, a furnace heats steel bars to 1635 degrees Celsius, well beyond the melting point. Meanwhile, another furnace heats the molds to 980 degrees Celsius. This burns out any remaining wax. It also fires the ceramic, making it strong enough to withstand molten metal. The pouring technique is critical. The metal must flow at a consistent rate to prevent the formation of air bubbles. After 5 hours, a pneumatic hammer breaks apart the mold. Workers saw off the gates and runners, separating the club heads. Then they grind off the last remnants of the gates and runners. A turntable runs the club heads through a sandblaster, which gives the metal a particular finish. Next, they stick on a metal badge bearing the club's model name. They apply a dot of automotive paint. The color identifies the angle of the club. There are 12 different angles. Now they line the neck of the club head with epoxy. Then coat the end of the shaft with epoxy and slip it into the neck. A pneumatic hammer pushes the shaft in as far as it can go. The shaft is made of either extruded steel or carbon fiber. Now it's time to work on the shaft. First, they cut it to the right length, depending on the model. Then they put the shaft on a spindle and wrap the top 25 centimeters in double-sided tape to hold the club's rubber grip. They lubricate the tape and the inside of the grip before sliding the grip over the shaft. A laser line helps them align the grip in the right position. This is critical because the grip is the golfer's guide to correct hand positioning, which is essential to a good swing. Next, a computer reads the lie, the term for the club head's angle relative to the ground. Then it reads the loft, the term for the angle of the club head's face. The computer then tells the technician what adjustments to make. Once he's made the adjustments, the computer reanalyzes the new loft and lie to ensure they're perfect. Finally, the golf club goes for a weigh-in. The scale shows that this club needs another 18 grams to bring it up to spec. So they affix an 18-gram weight made of thermoplastic and metal. Actually, it weighs slightly less than 18 grams because they factor in the weight of the epoxy glue. It's this type of precision that ensures these golf clubs fit the quality specifications to a T. The waffle started out in the Middle Ages as a flat wafer made not from wheat flour, but from oats or barley. As its popularity spread throughout Europe, many variations of shape and recipe developed. The introduction of leavening ingredients gave rise to the fluffy honeycombed breakfast cake we know today. The introduction of frozen waffles in the 1950s marked the dawn of a new era for these breakfast batter cakes. Making your morning waffles was suddenly a snap. All the big prep work takes place at the factory. They add flavorings like berries to a flour-based waffle mix, and then turn to the liquid ingredients: water, canola oil, and liquid cane sugar. They pour them into a big tank and mix thoroughly. Then they're ready to thicken it into a batter with the flour-based waffle premix. It also includes baking powder, which reacts with water to cause pockets of carbon dioxide to form, for a leavening effect that will continue during baking. After adding more berries, this batter is complete, and there's enough in this one tank to produce 3,600 waffles. Hot waffle irons move past a sprayer for a misting with a non-stick coating. Down the line, an automated pump deposits measured amounts of batter onto each grid plate. The top grid plates encase the batter. This production line is computerized, which ensures the plates are filled quickly and without any spills. As they move towards the oven, the waffle irons rotate, allowing the batter to reach all the crevices inside. They now move through a long gas oven. It takes about 2 minutes for them to cook. They emerge from the oven piping hot, where a machine called a picking drum removes them from the irons. As the picking drum revolves, needles grab the waffles and pull them off the hot grid plates. The picking drum transports the waffles up to another level. The needles retract, transferring them to a series of conveyors. At the other side of the factory, the waffles enter a blast freezer. The temperature inside is -7 degrees Celsius. Fans blow frigid air onto the waffles as they spiral through the freezer. It takes just 20 minutes to freeze and preserve these freshly baked waffles. The frozen waffles now merge into lanes to be sorted for stacking. A kind of trapdoor system releases them 3 at a time to grippers that move them onto a conveyor. The conveyor lane narrows, which forces the waffle stacks into a single row. A sensor-activated gate releases the stacks, 2 at a time, to the packaging station. It takes just a second for the 2 stacks of frozen waffles to be wrapped and sealed in a tight cellophane packet. Then it's into a metal detector. To demonstrate how it works, we place a quarter on one of the packages. The system senses it immediately, and a blower blasts the package off the conveyor. Suctioning fingers now pick up the outer paperboard box and open it as they place it on the conveyor. A ram then shoves the wrapped waffles into the box. Incredibly, they churn out more than 8,600 waffles an hour at this factory, catering to different tastes and dietary requirements. And that merits a toast. Much of today's high-tech equipment requires specialty wires and cables. From stage lighting to medical devices to robotics, wires and cables have to be custom designed and expertly manufactured to perform in a specific way and withstand various environmental conditions. Cables can be designed to withstand high temperatures or perform special functions, such as sensing pH levels or proximity to objects. At the heart of a cable are electrical wires, called conductors. A conductor begins as a bare copper wire. This extrusion machine coats it in plastic. Chilled water solidifies the plastic around the wire as insulation. This isolates each wire from its neighbors. Every conductor passes through a machine called a spark tester. It runs current through the conductor to ensure the insulation is flawless. If there's even the smallest break in the insulation, the machine will sound the alarm and locate the spot. The conductor then enters a machine called a cabler. It unrolls spools of insulated conductors and unites them with other components to form the cable's inner workings. At the center of this particular cable is a twisted pair of insulated conductors. Around them go color-coded insulated conductors and fillers to fill in the gaps between the conductors, giving the cable a smooth, cylindrical shape. Here, the fillers are strands of polypropylene foam. An orientation plate aligns the components in the proper configuration as they enter the cable assembly die. The components exit the die with the fillers wound around the insulated conductors, which wrap around the central wire. The next machine, called a taping head, wraps binder tape around the cable. This tape holds everything tightly in position so that the assembled components don't unravel. This is a different type of cable assembly machine. Like before, all the insulated conductors unroll from their reels and travel through the holes of an orientation plate. Dies divide the 6 conductors of this cable into 3 groups of 2, twisting the conductors of each pair together. The machine then wraps each twisted pair in a shield made of aluminum-coated polyester. Shielding eliminates what's known as crosstalk, signals interfering with each other. The next die joins additional wires that don't need to be shielded to the shielded ones. Then everything gets twisted into one cable. Then a final twisting, seen here in slow motion. The actual speed is 1,000 revolutions per minute. The next machine wraps tissue paper around the cable. Then an extruder applies a jacket made of a plastic and rubber compound. The tissue paper acts as a separator, preventing the jacket from sticking to the cable inside. Sometimes, instead of tissue paper, the cable runs through a bath of talc. Talc is a mineral that absorbs heat, so, just like tissue paper, it prevents the jacket from sticking. Once again, as the cable exits the extruder, chilled water solidifies the molten material into a jacket. A wheel with raised lettering imprints the manufacturer's name and technical specifications into the jacket. Certain jacketed cables need a braided shield to eliminate electrical interference. This machine has 48 carrier spools. each of which holds 10 wires made of tin-plated copper. As the jacketed cable moves upward through the machine, the spools move in a programmed pattern, weaving the shield around the cable. From there, a last trip through the extruder for a final thermoplastic jacket. And the custom-made cable is ready to be connected and powered up. Train wheels are used on rail cars around the world. Passenger trains rely on them to transport people. Freight cars depend on them for hauling products. And the locomotives that pull these trains and freight cars count on them to keep people and products moving smoothly. This company has been making train wheels and axles for over 150 years. To start, an electric furnace melts recycled steel at about 1600 degrees Celsius. A gigantic bucket transfers the liquid metal into what's called a mold pit. Inside the pit, the metal fills 8 molds from the bottom up, creating steel ingots 6 meters long. A bandsaw cuts the cooled ingots into sections called wheel molds. Each mold weighs about 450 kilograms. To prepare the molds for forming into train wheels, automated machinery loads them into one door of this rotary furnace, and they exit the other side at some 1300 degrees Celsius. A machine then places the molds into a high-pressure water descaling unit that removes the outermost layer of metal. A press then squashes each mold like a marshmallow with 9,000 tons of pressure, forging it into the rough shape of a train wheel. The train wheel is 76 centimeters in diameter when a robot removes it from the press and delivers it to a rolling mill. The mill squeezes and shapes the wheel until it expands to 91 centimeters in diameter, a 20% increase. The train wheel then enters a final shaping press that punches out the hole where the axle will go. All excess material goes back to the melt shop for recycling. After heat treatment, a machine sprays the outside of the wheel with cold water, which hardens the steel. Next, they machine the rim of the wheel and the axle hole. A worker then ensures they meet all specifications. Identified and labeled, the wheels are now ready for the axles. Axles start off as steel ingots that a manipulator feeds into a rotary forging machine. The machine rotates and hammers the piece, gradually shaping the hot metal into an axle. The manipulator and the forging machine work as a team, ultimately shaping the axle to the required diameter and length. The axles then go through a heat treating process. Next, they machine the entire axle, removing all excess material and preparing it to accept the train wheel. Here, a wheel mounting press fits a wheel onto each end of the axle. A worker lubricates the axle and attaches a bearing. He then bolts on the end cap and secures it using a torque wrench. A crimper tool locks the bolts in place. Finally, the mounted wheel set rolls off the assembly line, ready to install under a rail car.